Good morning. Today we want to talk about probability and counting. Probability is nothing more than quantification of uncertainty. Some experiments, some processes results into uncertain outcomes. If we can attach a number to that uncertainty, attaching a number, giving a numerical value to the uncertainty is what we call by quantification. So, probability is nothing more than quantifying uncertainty. So, let me give you one example, then we'll look into the other examples here. Let's say we toss a coin. That's a process, that's an experiment. Now, when we toss a coin, I have a coin here. If we toss a coin, there is uncertainty. It could be a head, it could be a tail. Now, if we attach a number to describe the uncertainty, that is what we call probability. So, when we are tossing a coin, we say there is a 50% chance of it coming as a head and 50% chance of it being a tail. That means that 50% is the quantification of the uncertainty of being head or tail. The process of quantifying that uncertainty like 50% in this example is what we call probability. Well, so probability has to do with experiments or processes like tossing a coin, that was an experiment. So, we can have single stage experiment and multi-stage experiment. So, let us look at some of the example of the single stage experiment. Toss a coin. If we toss a coin, that is a single stage experiment. We toss a coin, and the if we toss a coin, one of the natural question that might come is what is the probability of getting a head. So, if we are tossing a coin, a natural question will be what is the probability of getting a head or what is the probability of getting a tail when we toss a coin. Tossing a coin is the experiment, and this is a probabilistic question associated with that experiment. Well, another one stage experiment could be roll a die. Roll a 6-face die that has 1, 2, 3, 4, 5, 6 written in space. So, we have a 6-face die, and that is an experiment. Rolling a 6-face die is an experiment, and the question will be what is the probability of getting an even number. What is the probability of getting an even number if we roll a die? Rolling a die is an experiment. One probabilistic question could be what is the probability of getting even number. Well, a little more complex, a little more complicated experiment could be rolling 2 dice. Roll the 2 dice, and if we roll the 2 dice, one of the question could be what is the probability of getting a number whose sum is 5. So, we get something in first die, we get something in the second die. What is the probability that sum of the 2 numbers is 5? That will be a probabilistic question. So, in order to answer this question, we have to go through some vocabularies. Let us see what are these vocabulary. One of the very frequently used vocabulary when we talk about probability is called outcomes. Outcomes are nothing more than the result of the experiment. So, when we toss a coin, if we think tossing a coin is an experiment, so toss a coin, if we think this is an experiment, the outcomes are head or tail. Outcome could be head, outcome could be tail. If we roll 2 dice, then the outcomes will look like this. One in the first die, one in the second die. That is one of the possible outcome. Well, it could be 1 in the first die and 5 in the second die, another possible outcome. Well, it could be 3 in the first die and 4 in the second die. That's another possible outcome. So, outcomes basically means the result of the experiment. Now, another vocabulary that comes quite frequently is called sample space. Sample space is nothing more than collection of all possible outcomes. We do an experiment, and if we make a list or a collection of all possible outcomes, that is what we call sample space. For example, if we are tossing a coin, if the experiment is toss a coin, if this is my experiment, then the sample space, we write S for the sample space, uppercase S represent the sample space. This is nothing more than the head is one of the possible outcome, tail is the possible outcomes, head and tail makes the collection of possible outcomes, so the sample space is head and tail. Now, if we roll a die, a single die, then the sample space in this case will be, we may get 1, we may get 2, we may get 3, we may get 4, we may get 5, we may get 6. That's the sample space. Well, if we roll 2 dice now, if we roll 2 dice, the sample space will be a little complicated. Roll 2 dice, the sample space will look like this. The sample space will be 1 in the first die, 1 in the second die. That's one of the possible outcome. 1 in the first die, 2 in the second die, 1, 3 in the second, 1, 4 in the second, 1, 5 in the second, and 1, 6 in the second. Similarly, 2 in the first one, 1 in the second, and so on, we continue. So, we will have 6, 1 and 6, 2 and so on, 6, 6. There will be 36 altogether possible outcomes. This is what the sample space when we roll 2 dice will look like. So, basically sample space means listing or collecting all the possible outcome associated with an experiment. Now, another vocabulary, another word that comes quite frequently in probability is event. Events are nothing more than subset of sample space. Subset of sample space are called events. So, for example, let us say roll a die. Suppose we are rolling a die. Suppose this is the experiment we have in our head. An event could be this. Let us say E1 is an event. This E1 is even numbers. E1 is the event of getting even numbers. That means we are thinking of this subset 2, 4 and 6 out of the sample space, which is 1, 2, 3, 4, 5, 6. So, event is basically a subset of the sample space, and well, similarly we may say E2 is getting less than 4, which will be 1, 2 and 3. This is also a subset of the sample space. So, event are basically a sub collection, a smaller set in general than the sample space. Well, one more vocabulary here says equally likely outcomes. When we do experiment, if every outcomes have the same chance of happening, the outcomes are equally likely. For example, if we toss a coin, the chance of getting a head and chance of getting a tail are same. So, head and tail, they are called equally likely outcomes if we toss a coin. Similarly, if we roll a die, then we might get 1, we might get 2, we might get 3, we might get 4, 5 or 6, and all of these numbers have the equal chance of happening. The chance of getting 1 is the same as the chance of getting 5. So, this kind of outcomes, getting anything 1, 2, 3 or 4 or 5 or 6, when we roll a die, they are called equally likely outcomes. When outcomes are equally likely, probability of an event, I will write this way, probability of any event E is an event, probability of event E is number of outcomes in E. We will count how many outcomes are in the event, and we divide that by number of outcomes in the sample space. So, I will write S for it. S represent the sample space. So, if we divide number of outcomes in an event with all total number of possible outcomes, then we get probability of an event. Let us look at few examples. So, the example 1 talks about tossing a coin and what is the probability of getting a head. So, let us think of the sample space is head or tail. Now, probability of getting a head means we are thinking the event of interest in this question is head. Probability of getting a head means the event of interest for this particular problem is head. So, using this formula, probability of that head is number of outcomes in E, which is 1, there is only one outcome which is head, and number of outcomes in the sample space we count 1 and 2, so 1/2. Probability of getting a head is 1/2. Well, let us look at another example. What is the probability of getting an even number if we roll a die? Now, we are rolling a die. So, the sample space as talked before is 1, 2, 3, 4, 5 and 6, and the event of interest in this particular problem is even number, which is 2, 4 and 6. That means probability of that particular event 2, 4 and 6, which is the probability of even number, is given by, we count how many outcomes are here, 1, 2 and 3. So, 3 divided by total number of outcomes is 1, 2, 3, 4, 5, 6. So, there are 6 of them. So, again it is 1/2. Let us look at another question. What is the probability of getting numbers whose sum is 5, and in this case we are rolling 2 dice. So, in this case the sample space will be as discussed before 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 and 2, 1, 2, 2 and so on, and similarly 6, 1 and so on 6, 6. There will be 36 total outcomes. So, that will be the sample space. Now, the event of our interest in this case is those outcomes for which the sum is 5. Sum is 5 means if we add the 2 numbers here, we should be getting 5. So, 1, 1 will not be an outcome for that particular event. 1, 2 will not be an outcome because 1 plus 2 is 3. So, we have to find out those outcomes where the sum of the 2 numbers is equal to 5. So, you see it is 1, 4. What else? Well, there will be 2, 3 in this list. 1, 4, there will be 2, 3 and there will be 3, 2. There will be what else? 4, 1, 1, 4, 2, 3, 3, 2 and 4, 1. Think of any other outcome that is giving sum equal to 5. I think that is all. So, this is our event of interest, sum is 5. So, by our formula, probability of this event is, we count number of outcomes 1, 2, 3, 4 divided by, as already said, the total number of outcomes in the sample space is 36. So, it will be 4 over 36, that is nothing more than 1 over 9. So, the idea is very simple. When the outcomes are equally likely, in order to calculate probability of any event, count number of outcomes in the sample space, or count how many total possible outcome, and count how many outcomes in the event of our interest, and divide those two numbers. Now, sometimes when we calculate probability of event, we will have little compounded kind of event. Two events will be combined. So, let us say A is an event and B is an event. If we want to find probability of A union B, remember our set theory, union refers to OR. If we want to find probability of happening event A or event B, then it is nothing more than probability of event A plus probability of event B minus probability of event A intersection B. Intersection is AND. So, we add the probability of A and B and subtract the probability of both. Now, if two outcomes are disjoint, that means they do not have any common outcomes in them, then those two outcomes are called disjoint, or those two events, those two events are called disjoint event. If there is nothing in common, this will be 0, there will be no intersection, so the probability of intersection will be 0, and in case of disjoint outcomes, or in case of when the outcomes are disjoint, we call them mutually exclusive event. When the events are disjoint, we call them mutually exclusive event, and in the case of mutually exclusive event, the probability of A or B, union is OR, probability of A or B is simply probability of A plus probability of B. Well, there is one more rule, that rule talk right now is a very famous rule called addition rule in probability. Another important rule in probability is called complement rule. So, if event A and B are complementary means A and B combiningly gives the entire sample space. Two events are called complementary events if their union is entire sample space. So, two events are complementary if they are disjoint, they have to be disjoint, and their union has to be the entire sample space. So, if we already know what do we mean by complement from our set theory. So, complement, if two events are complementary, probability of event A plus probability of event B has to be equal to 1. The sum of probabilities of two complementary events has to be equal to 1. That is what we call complement rule. Let us look at an example. Suppose we are rolling two dice. What is the probability of getting numbers whose sum is 2 or 4? So, we have this one event E, let us say E1 equals sum is 2, and another event is E2, the sum is 4. Now, we want to find out probability of E1, 2 or 4, or means union E2. So, we want to find this probability of E1 union E2. According to our addition rule, probability of A union B is probability of A plus probability of B minus probability of their intersection. So, we will apply the same rule here. So, probability of E1 union E2 is nothing more than probability of E1 plus probability of E2 and minus probability of E1 intersection E2. Let us see how much we will get. Probability of E1. E1 is sum is 2. We are rolling two dice. The total outcome is 36, which we know for sure. So, the denominator has to be 36. Now, in the numerator, we have to think of how many outcomes will give us 2 as a sum. 1 1 will give 2. Anything else? Nothing else will give 2. So, this is 1 out of 36. There is only one outcome out of 36 outcomes that will give us the sum equal to 2. Now, this is a probability of E1 plus probability of E2. E2 is sum equal to 4. Let's think of outcomes that will give us sum equal to 4. 1 3, 3 1 and 2 2. 1 3 will give sum equal to 4, 3 1 will give sum equal to 4 and 2 2 will also give sum equal to 4. So, that means we have 1 3, 3 1 and 2 2. So, there are 3 outcomes. So, 3 divided by 36 and minus. Now, in order to get a sum equal to 2, in fact, our E1 is 1 1. That is E1, that will give us sum equal to 2, and E2 is 1 3, 2 2 and 3 1. Now, you see, do they have any outcome in common? They do not have any outcome in common. E1 and E2 does not share any common outcome. That means they are disjoint sets. When they are disjoint sets, the probability of their intersection, E1 intersection E2 will be 0. So, our result is 1 over 36 plus 3 over 36. If we add them together, it is going to give us 4 over 36, which is, well, again 1 over 9. Let us look at one more example. What is the probability of getting a number whose sum is more than 3? So, now we want to know the probability of getting a number whose sum is more than 3. Probability of getting a number whose sum is more than 3. We are rolling 2 dice. So, the event right now, event E1, the event E1 let us say is sum more than 3. If we want to think of all the outcomes in this event, if the sum is more than 3, it could be 1 3. 1 3 will give us 4. So, 1 3 is fine. 1 4 is also fine. Now, there are bunch of other events that will give us sum more than 3. There are so many of them. Well, in order to solve this problem, I will think of complement of this. Sum more than 3, let me think of E2. E2 is less than sum is less or equal to 3. Sum is less or equal to 3. That means I am thinking of all the outcomes whose sum is either 3 or less than 3. So, 1 1 of course the sum is 2, which is less than 3. 1 2 of course the sum is 3, equal to 3 is fine, and 2 1. There will be no other outcome where the sum is less or equal to 3. See, now E1 and E2, they are disjoint, they do not share any common outcome. If we take their union, E1 union E2 will be the entire sample space. That means E1 is complement of E2. In this situation, we say E1 is complement of E2. So, in order to calculate probability of E1, we can use our complement rule. According to complement rule, if 2 events are complementary, sum of their probability has to be 1. So, I will be using the complement rule here. Because of complement rule, we can say probability of E1 plus probability of E2 has to be equal to 1. That is the same thing. Well, probability of E1, I do not know how many outcomes in E1, so I do not want to count that, but probability of E2 is easy to find because there are only 3 outcomes in it. So, this is probability of E1 equals probability of E2 is, well, plus I mean, plus probability of E2 is 3 out of 36 equals 1. So, that means probability of E1 will be 1 minus 3 out of 36, which will be 33 out of 36, something like this. So that's how we can use complement rule in order to solve some probability problems. Well, let's look at one example where we have a table with bunch of information is given and we want to solve some probabilistic question. So this says consider the information given below. Probability of disease symptoms. Fever is 0.2, rash is 0.3, fever or rash is 0.4. So if somebody comes to the clinic for a diagnosis of a particular disease, there is 0.2 means 20% probability that the person will have a fever. There is a 30% probability the person will have a rash, and there is a 40% probability the person either have a fever or a rash. The question is, what is the probability of fever and rash? What is the probability a person will come for the diagnosis of the disease and the person will have both fever and rash? So we can say here, let's say F for fever and R is for rash. So I'll be using S to represent the event of fever and R for the event of rash. So according to our addition rule, probability of fever union rash. Union stands for OR, by the way. So probability of fever or rash according to our addition rule of probability. Let's go back and look at the addition rule of the probability. The probability of fever or rash is probability of fever plus probability of rash minus probability of fever and rash. So I'll be using that formula to solve that problem. So this is probability of fever or rash equals probability of fever plus probability of rash minus probability of fever and intersection means and rash. Let's fill in this equation with the number according to the given information in the table. According to the given information in the table, fever or rash is 0.4. Probability of fever or rash, this is 0.4 equals probability of E, no E, there is F, sorry. So probability of F, fever is 0.2 and probability of rash is 0.3 and minus probability of F and R. Well, now this is a simple equation, we can solve it. So let me solve it here. The left hand side is 0.4, the right hand side is 0.2 plus 0.3 is 0.5 and minus P F intersection R. If we solve this equation, P F intersection R, fever and rash will be equal to 0.5 minus 0.4, which is simply 0.1. Okay, probability of fever and rash, solving this equation, we will get probability of fever and rash equal to 0.5 minus 0.4, which is simply 0.1. Okay, now there is one more vocabulary that comes when we talk about probability, and that's called odds. Odds are very, very close to probability. However, they are not exactly probability. There is a slight difference between odds and probability, and we will see here. Okay, when we think of odds, we always think of odd in favor of an event and odd against an event. So odd in favor of an event is nothing more than number of outcomes in the event divided by number of outcomes not in the event. So, when we calculate odd in favor of an event, it is number of outcomes in the event divided by number of outcomes not in the event. If we were calculating probability of the event, the numerator of this formula will remain the same, however, denominator will contain all outcomes. But when we calculate odd, we count only outcomes, they are not in the event of our interest. Well, odd against an event will be simply flip the numerator and denominator, outcomes not in the event divided by outcomes in the event. Okay. So, that is how we calculate odd. Let's look at one example. Let's say one example here. Let's say we are rolling a die. Roll a die. This is our experiment. If we want to calculate odd in favor of let's say the event 5, odd in the favor of event 5 is number of outcomes in the event is 1, number of outcomes not in the event. That means right now we are thinking of 5. The event of interest is 5. How many outcomes are there which are not 5? There are altogether 6 outcomes, 5 is one of them. So, there are 5 outcomes which are not 5. So, the denominator will be 5. Look, probability of 5 will be 1/6, but odd in the favor of 5 will be 1/5. Now, in the same question, if we want to calculate odd against 5, then it will be 5/1. Just flip the numerator and denominator for odd in favor to get odd in against. Okay, now let us talk about multi-stage experiment. Multi-stage experiment is like tossing a coin 4 times. Toss a coin, one stage, toss the coin again, second stage, toss the coin again, third stage, toss the coin again, 4 stages. So, tossing a coin 4 times is 4-stage experiment. In fact, if we roll a die twice, roll a die and see what comes, roll again the die again and see what comes. That is 2-stage experiment. Multi-stage experiment means we are repeating some experiment, we are repeating, we are doing, maybe we say, saying repeating an experiment several times might be incorrect, but we will be doing so many experiments. Tossing a coin once is an experiment, tossing it again is another experiment, and so on. That is called multi-stage experiment. In order to solve question related to multi-stage experiment, this one diagram very famously called probability tree will come very handy and very useful. What is probability tree? Let us think of the first one. Let us think of tossing a coin 4 times. So, in order to construct the probability tree for this multi-stage experiment, this is what we do. The first stage is tossing a coin once. This is stage 1. Well, I need a little bit of space. So, if we are tossing a coin 4 times, let's see, the first stage, stage 1 is tossing it the first time, stage 1. Stage 1 is tossing it first time. When we toss a coin the first time, we might get a head or we might get a tail. And we know there is half probability of being head and half probability of being tail. Now, stage 2. Stage 2 is to toss it again. If we toss it again, we might get head or tail. This is one half and this is also one half. And similarly, we might get head or tail here also. This is head, this is tail, one half and one half. Stage 3. Stage 3. Now, again head or tail. Again head or tail. Head or tail. And this is also head or tail. And the stage 4 will be again one more head and tail, and so on. This diagram is what we call probability tree. And if we construct probability tree, in order to get probability of any outcome, we simply have to multiply probability of each branch going to the outcome. So if I want to calculate probability of head, head, head and head, then we will multiply 1/2 times 1/2 times 1/2 times 1/2. Head, head, head and head. 1/2 times 1/2 times 1/2 times 1/2. So we will get 116. Probability of all 4 heads will be 116. That's what we call probability tree. We can think of a probability tree if we roll a dice twice. If we roll a dice twice, let's say roll a die twice, then the probability tree will look like this. Stage 1, we might get 1, we might get 2, we might get 3, we might get 4, we might get 5, we might get 6. So this is 1, 2, 3, 4, 5, 6. This is the stage 1. Now stage 2 will be, we might get 1, 2, 3, 4, 5, 6. Similarly here also 1, 2, 3, 4, 5, 6. Similarly this is 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Similarly this is 1, 2, 3, 4, 5, 6, and so on. This will be what the probability tree will look like if we want to construct it when we roll a die twice. And if this probability is 1/6 and this probability is also 1/6, if somebody says what is the probability of getting a 1 in the first roll and 2 in the second roll, we see, well, 1 in the first roll is 1/6, 2 in the second roll is 1/6, so that will be 1/6 times 1/6, so that will be 1/36. Anyway, let's look at one example of using this probability tree to solve a problem here. Okay, a box contains 2 red marbles and 1 green marble. There are 2 red marbles and 1 green marble. A marble is randomly selected and returned to the box. We will take one marble randomly, look at the color, put it back. And a second marble is selected. What is the probability of selecting 2 red marbles? So our question is, what is the probability of selecting 2 red marbles? In order to solve this question, I will use the concept of probability tree. So this is a 2-stage experiment because we take one marble and again we take another marble. So the first stage, when I take a marble, the result could be either a green, either a red or a green. That is my stage 1. Now, because there are 2 reds and 1 green, probability of getting a red will be 2 out of 3 marbles. Similarly, probability of getting a green will be 1 out of 3 marbles. There are 3 marbles in total, one of them is red, so 1 out of 3. Now, this is stage 1. Now, let us think of the stage 2. Let us think of the stage 2. In stage 2, because we are putting the marble back in the box, there will be still 3 marbles because we are putting the marble back. So, in the second stage, we might get red or a green, and probability of getting red is still 2/3 and getting green is still 1/3. The same thing here, red and green. So, this is red is 2/3 because two reds there and 1 green, so 1/3 here. So, the first outcome is red and red, the second outcome is red and green, the third outcome is green and red, and the fourth outcome is green and green. So, in this particular question, the question is what is the probability of selecting 2 red marbles? So, basically the question is what is probability of R and R, red and red. In order to calculate probability of red and red, we have to multiply probabilities of all the branches that goes to R and R. In order to go to R and R, from our starting point, we will take this branch, the probability of that branch is 2/3, and multiply by, again we will take this branch, probability of that branch is again 2/3, so it will be 4/9. This is how we can use the probability tree to calculate various probabilities. Well, we talked about addition rule of probability and we talked about complement rule of probability. We want to talk about one more rule of probability, which is called multiplication rule of probability. This multiplication rule of probability says if 2 events are independent. Independent means the event A does not have any probabilistic information about event B. They do not have a probabilistic connection. So, if 2 events are independent, then the probability of A intersection is, again remember intersection means and, probability of A and B is equal to probability of A times probability of B. To find probability of intersection of 2 events when the events are independent, simply multiply their probabilities. That is what this rule is saying. Let us look at one example here, and this example says what is the probability of rolling a die and obtaining a 4 and then rolling it second time and obtaining an even number. So, the question is this: probability of a 4 in the first roll and let me say even in the second roll. This is what our question is. So, this is probability of an event times probability of another event. This is basically AND means we are thinking of probability of intersection. Because the first roll, the outcome of the first roll of the die does not tell us anything about outcome of the second roll. Because the outcome of the first roll of a die does not tell us anything about the second roll of the die, these 2 events 4 and even, 4 in the first roll and even in the second roll, they are independent. Because they are independent, using the multiplication rule of probability, this rule of probability, this is the same thing as probability of 4 in the first roll times probability of even in the second roll. Well, in the first roll, what is the probability of 4? 4 is one outcome and there are altogether 6 possible outcomes, so it is 1/6. And probability of even in the second roll, if we think of even, there are 3 outcomes which are even, namely 2, 4 and 6. So, 3 out of total number of outcomes is 6. So, this is 3/36, or if we simplify, this is 1/12. So, the probability of getting 4 in the first roll and even in the second roll is 1/12. Okay, if a die is rolled 4 times, what is the probability of getting at least 1/6? So, now we are doing 4 stage experiment. A die is rolled 4 times and our question is what is the probability of getting at least 1/6. So, the event right now is at least 1/6. I will think of another event, let us say E2, which is no 6. So, E2 is saying we roll the die 4 times and we do not get any 6. Now, E1 and E2, these two events, they are complementary. No 6 plus at least 1/6 will make the entire sample space. So, they are complementary events. So, in order to calculate probability of E1, I will use the complement rule. According to the complement rule, because E1 and E2 are complementary, probability of E1 can be written as probability of 1 minus E2. Okay. So, 1 minus E2, E2 is no 6. No 6 means the first one is not 6 and the second one is not 6 and the third one is not 6 and the fourth one is not 6. None of the roll will give us 6, that means no 6. So, this is no 6, first is no 6 and again probability of first is no 6 and means intersection, again no 6, intersection, again no 6, intersection, again no 6. As already explained in the previous problem, probability of the outcome of the first roll does not tell us anything about outcome of the second roll of the die. So, all these 4 events are independent. So, we can use the multiplication rule, and this is probability of no 6 in the first times probability of no 6 in the second times probability of no 6 in the third and probability of no 6 in the fourth. Now, this is 1 minus probability of 6 is 1/6, probability of no 6 means anything other than 6, that means 1 over, this is 5 over 6 times 5 over 6 times 5 over 6 times 5 over 6. So, if we simplify this, we will get 1 minus, well, 5 times 5 times 5 times 5 divided by 6 times 6 times 6. So, that will be 5 to the 4th over 6 to the 4th. I will let you do the simplification and find the probability. That will be 5 raised to the 4th divided by 6 raised to the 4th. Okay. Another concept that comes in probability theory is called expected value. Expected value is average if an experiment is repeated several times. For example, if this is the question we are thinking of expected value, what is the average if a die is rolled 1000 times? If we roll a die 2 times, let us say, so the first one is 1, the second one is 2, or let us say 3 times, and the third times we got a 6. Let us say we roll the die 3 times, the first time we got 1, the second time we got 2, and the third time we got 6. The average of this 3 will be 1 plus 2 plus 6 divided by 3, which is 6 to 8, 9. So, average of this 3 is 3. Well, if we roll the die 4th time, we do not know what it gonna come and we do not know how much is the average. So, for if we repeat an experiment for a small number of times, then the average cannot be predicted. We do not know how much will be the average. For example, rolling 3 times, let us say I had gotten 1 in the first, 1 is the second and 1 in the third, then the average will be simply 1. However, if an experiment is repeated many times, we can predict, we can tell how much will be the average of the outcomes. That value is called expected value. Okay, the formula that is used to calculate expected value is sum. This is, in words, this is sum of the values x and corresponding probability. If we multiply the values with corresponding probability, if we multiply the values with corresponding probability, then we get the expected value. So if we want to solve this question, what is the average if a die is rolled 110,000 times, or basically if the question is what is the expected value if we roll a die. Let us say the question is this: what is expected value if we roll a die? This means if we roll the die so many millions and millions times, what will be the average of the numbers that we will get on those experiments? If we want to solve this, we will use this expected value formula. What it says is calculate the sum of x and px. So what does that mean? If we roll a die, we might get 1, multiply by the probability of getting 1. Probability of getting 1 is 1/6. Another outcome, possible outcome is 2, multiply it by its probability, which is 1/6. So I am writing the values and multiplying by the corresponding probability and adding them up. Similarly, 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 and plus 6 times 1/6. So this will be equals, 6 will be the common denominator. In the numerator we will get 1 plus 2 plus 3 plus 4 plus 5 plus 6, 7, 7, 14 and 7, this will be 21 divided by 6. So this will be 3.5. So that means if we roll a die millions time, the average of the numbers we are going to see will be 3.5 or close to 3.5. That's what it means. Let's look at one problem we use concept of expected value to solve, and this is a lottery problem. So a lottery game has 8 hidden dollar amount that might be any of the following. So the hidden dollar amount here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, well, I don't know why I said. Let's say there are only 8. Okay, my lottery and this information looks like inconsistent, but that's okay. Suppose there are $8 amount 1, 2, 3, 4, 5, 6, 7, 8. In fact, if we change this to 9, it does not matter. And the amounts that are hidden are $50, $20, $5 or $1. So that means if we scratch this, either we're going to see a 50 or a 20 or a 5 or a 1. If you have 5 identical amounts, so out of this, if 5 of them are identical, you will win that amount. You will win that amount. So if I get this is a 50, 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 that means I get 50. I win 50. If this is a 1, this is a 1. If 5 of them are 1, then I'll win $1. That is how the game is going on. So now what it says is there is also a $10 bonus amount if a sun symbol is rebelled. So if any of this is a sun, then we will win $10 as a bonus. Looks like a good lottery ticket. Suppose the probability of winning $50, $20, $5 and $1 or the bonus are 1 over 500. So it's given to us that probability of winning $50 in this lottery game is 1 over 500. Probability of winning $20 is 1 over 200. Probability of winning $5 is 1 over 50. Probability of winning $1 is 1 over 10. And probability of winning the bonus means basically $10, is 1 over 200. So probability of winning each amount is given to us. Now the question is, what is the expected earning of the game? If you play this game, if you play this game for many times, 1 million times, what amount should you expect to earn? If you play only once, you might earn $1 or you might earn nothing. If you play the second time, you might earn $5, $1, $20, $50 or nothing. However, if you play it so many times, on average we can calculate how much we should expect to earn, and that is what called expected value. And in order to calculate expected value, as already said, you have to multiply the values by the probability. So according to this question, the win amount will be $50 times the probability of $50 as given in the question is 1 over 500. So 50 times 1 over 500 plus we might win $20 and its probability is given to be equal to 1 over 200, plus we might win $5 and its probability is given to be equal to 1 over 50. We might win $1 and its probability is given to be equal to 1 over 10. And we might win $10 and its probability is given to be equal to 1 over 200. Okay, if we add these numbers, then we're gonna get well, $0.45. I'll let you do the calculation. This will be equal to 0.45. So the expected earning of this game is 0.45, 45 cents. Well, another question says if the cost of each ticket is $1, if we need to pay $1 to buy this ticket, is it a fair game? When we have games, lottery games, we say they are fair games if the probability of winning and the amount of the expected win and expected loss are equal. That means the game is fair if expected earning is 0. My expected earning is 0 means the expected earning of the lottery company will be also 0. Nobody will be winning, nobody will be losing. If there is a game where nobody wins, nobody loses, that's called fair game. So the question is this if cost of each ticket is $1, is it a fair game? Now on average, because each ticket is $1, on average you'll pay $1 for the lottery, and on average you will be winning 0.45, 45 cents. So because win is 45 cents and loss is $1, because the win amount and the loss amount are not the same, this game is not fair. This game is not fair. If the win and the loss is same, we say this is a fair game. Example of a fair game will be to toss a coin and do a betting. Head you win, tail I win. So if we calculate the expected value of win or loss in that game, head I win, tail you win, then the expected value will be 0, because if we play this game for longer number of times, neither you will win nor I will win. That's a fair game. All right, if you have any question, email me, let me know. Thank you for watching. Have a good day.